Hello and welcome to Physics Platter. In Physics Platter, today we are going to talk about lenses. Thanks to some devices that we use every day, we are pretty much familiar with the lenses. For example, we use specs to rectify the eye problems. We know that there are lenses in the camera, and then we also sometimes often use a magnified glass. Okay, these are all examples of lenses, different types of lenses, and there are more like telescope, the microscope. All the devices use lenses. Okay, so lens, we can define lens as an optical device. Of course, it is an optical device made of a transparent object. Of course, it has to be transparent because the light has to go through it. So an optical device which is made of a transparent object which is bound by two surfaces, one of which is a spherical surface. So this is an example of a lens. Actually, a couple of lenses we are all carrying with us all the time from the birth. That means eyes. There are lenses in the eyes, that's why you can see. Anyway, so there are two types of lenses: convex lens and concave lens. A lens whose the middle part is thicker than the two edges is called a convex lens. A lens whose middle part is thinner than the two edges is called in this case is called the concave lens. In this case, the middle part is thinner than the two sides. So such a lens is called the concave lens, and a lens whose middle part is thicker than the two sides or two edges is called the convex lens. Let's talk about the convex lens first. Let's see. Convex lens, or this is also called converging lens. It is also called a converging lens. Alright, so concave lens is a lens, as I told you, whose middle part is thicker than the two edges. There can be several types of concave lens whose two surfaces, both the surfaces can be spherical. Such a lens is called the biconvex lens. Biconvex, and then there can be a lens whose one surface is plane and another surface is spherical. Such a lens is called the plano-convex. Plano-convex lens, and then there can be lens whose one surface is concave and the other surface is convex, just like the moon, half moon rather. Such a lens is called the concavo-convex lens. Okay, so biconvex, plano-convex, concavo-convex. There can be three types of convex lenses. Now let's draw a big convex lens. The most used convex lens is the biconvex lens, whose both the surfaces are part of a sphere and most commonly similar spheres. Now, exactly the midpoint of the lens is, let's say this point is O. This midpoint is called the optical center. Optical center of the lens. Now because the two surfaces are part of a sphere, we can, let's say this is one of the spheres and this is the other one. Let's say this is the other one. Two spheres must have centers. This one and this one. Both the spheres must have a center. Let's say this is C1, this is C2. So OC1 is the radius of curvature of the one of the spheres, and OC2 is the radius of curvature R2 for the second sphere. This C1 and C2, if we join the two centers, center of the spheres by a straight line, then this line goes to the optical center of the lens. This line C1 and C2, this line C1, C2 is called the principal axis of the lens. So what is principal axis? Principal axis of a lens or the convex lens is the line joining the two center of curvatures of the lens, which goes to the optical center of the lens, is called the principal axis. Alright. Okay, so optical center, principal axis, radius of curvature and the center of curvature. These are the terms involved with a convex lens. Alright. Now let's move on to the point. As I told you, a convex lens is also called a converging lens. Converging lens. Why? Just because a convex lens converges the rays of light. But why does it converge? We will see that. Okay. Let's draw a lens here. Now, and let's draw the principal axis, something like this. Now, a convex lens can be divided in such a way that it can be considered as combination of several prisms. For example, this becomes a prism. Again, this is also part of a prism, right? Similarly, in this side, we can divide the lens into several parts. And the smaller parts can be considered as the prisms because they are made of the transparent material, right? Now, in the previous lectures, we have seen that in a prism, a light ray moves or bends. Let's say A, B, C is the prism. After getting refracted by the prism, it bends towards the base. In this case, BC is the base and it always bends towards the base of the prism. Okay. So in this case also, let's consider a paraxial beam falls. Let's consider, oops, come on, yeah. A paraxial beam falls on the lens, top of the lens. Then actually it falls on this prism, right? And after getting refracted by the prism, it will bend towards its base. Now this is the base of the prism. That means after getting refracted, it will bend towards the base and it will go like this. Alright. Similarly, another ray which falls on the second prism will also bend towards the base, right? And a ray which goes through the principal axis, let's say through the principal axis, falls on this part of the prism. Now see, this part of the prism, this part of the lens is actually a slab, a glass slab, we can say, and the ray of light falls normally on the slab. That means it will not bend anywhere, but it will go straight. It will just go through the slab in the same path that it was coming in. Alright, and then it will get refracted. Okay, in the other part of the lens also, the ray will get bent towards the base. Now we'll see, in this part the lens is this one and this is the base in this part. So the ray this time will bend towards this side, towards the principal axis. Similarly, in the last part also, in the bottommost part also, the ray will bend like this. Alright. So we can see that a paraxial beam, when goes through a convex lens, when a paraxial beam goes through a convex lens, actually after getting refracted by the lens, they converge. That's why it is called the converging lens also. Converging lens also. Okay. Now when the ray is a paraxial ray, they converge to a point. They all converge to a point, a single point, and this point is called the focus. This point is called the focus of the lens, F. This point is called the focus of the lens, F. Alright. Now when a paraxial beam, after getting refracted by a convex lens, converges to a single point, this point is actually called the second principal focus of the convex lens, which is denoted as F2. Alright. Now what is the first principal focus then? Of course, we have drawn the light is coming from the left hand side in this case. Light can come from the right hand side also, right? And from the property of the reversibility of light, we can imagine that such a focus must be present in this side also, in the other side of the lens, right? But while defining the first principal axis, let's say this is defined in such a way that just remember the reversibility of light. In the previous case, a paraxial beam was coming and after getting refracted by the lens was converging to a point, which is a second principal focus. Now, if we consider a point from which a diverging beam comes, or if we keep a point source at a point on the principal axis, then the light coming from it will be diverging, right? Now if there is a point from where a diverging beam comes and after getting refracted by the lens becomes paraxial, after getting refracted by the convex lens becomes paraxial, that means parallel to the axis, such a point is called the first principal focus. First principal focus of the lens. Okay. So basically first and second principal focus for a regular convex lens is nothing but shows the reversibility of light. Okay. Alright. Now let's move on to the image formation. Let's discuss about the image formation of light. Image formation by the lenses. Here one thing must be understood, that light consists of, let's say white light consists of different frequencies, right? So different colors of the lights are actually different frequencies of the light. Now different frequencies of the light bend at different angles because the refractive index of a material depends on the color of the light. That means the bending or deviation of the light will be different also for different colors of the light. Okay, so here one thing must be considered, that all the ray is a single beam of single color must be considered. So ray of lights with the single color or single frequency must be considered while talking about the definitions of this focus and so on. Okay, so this focus, actually focal distance or whatever, depends on the frequency of the light. If the frequency changes, the focal length will also change here. Okay, by the way, here we can also, let me introduce some other terms also here. We have said the O as the optical center, F1 is the first principal focus, F2 is the second principal focus. Now OF, the distance of the focal point from the optical center, is called the focal length of a lens. Focal length of a lens. Alright. Okay. Now let's talk about the image formation by a lens. Image formation by a convex lens. Image formation by a convex lens. To learn the image formation by a convex lens, let me draw a convex lens first. First of all, we have to draw the lens, and then the way I like it, second thing we do is to draw the principal axis. Okay, now point the optical center of the lens, and then point the focus, two foci in the two sides, and then another 2 points which are at the distance 2f. Let's say P and Q are the points F1, F2, then O F2 equals to F2Q equals to F, the focal distance, equals to O F1 equals to F1P. Okay, that means O P equals to O, Q equals to 2F. Okay, so these are the 4 points we need to draw the image of an object by a convex lens or concave lens also, we can say. Now what we will do, we will position the object at different positions, and then we will see where the image is formed. Alright, before that, few things that we should know. First of all, any ray which goes through the optical center of a lens goes undiverted. That means it does not bend, it goes straight in any direction. If it goes through the optical center, it will go in the straight line without bending. Alright, so this is one thing we must know. Secondly, any paraxial beam, a ray which is parallel to the axis, after getting refracted by the convex lens, will move through the second principal focus of the lens. Okay, so these are the two things, and anything that goes through the center, through the principal axis of the lens, will also go in a straight line. without bending anything, because it goes to the optical center, of course. Okay, so these are the things that we should know before we start drawing the image formation by the convex lens. Okay, so we will consider different positions of the object for which we will find where the image is formed. Basically, we will find the image formed by an object, an extended object, which we will name as AB, where arrow will represent the head of the object and the base will be on the principal axis. Now we will bring this object from infinite distance. First of all, we will consider the object to be placed at infinite, and then slowly we will go closer to the lens, and then we will see at different positions where the image is formed. Alright, so let's move on to the first condition, where the object is placed at infinity. Okay, so this is my convex lens, this is the principal axis, optical center, and then in this case, let's say light comes from the left hand side to the right hand side. An object, when the object is placed at an infinite distance, the ray coming from it is considered to be parallel rays. Alright, so we will consider that the object is placed somewhere in this side in the infinite distance. That means we will consider the ray which comes parallel to the axis. Let's say here is the focus. F. After getting refracted by the lens, of course a paraxial beam or paraxial ray will go through the focus of the lens. Another ray will draw that will also go through the focus of the lens. Okay, that means now we can draw infinite number of rays here, but all will go through the focus here, because all are paraxial beams only we can consider, because the object is placed at an infinite distance, right? Alright, so in this case we can say that what are the properties of the image? Here the image is formed, of course, by the convergent beam, where the beam meets at a point and the image is formed. That means the image will be real image. The image is a real image. Number 2, whatever is the size of the object, the image is a point image, right? The image is just a point. Just like if we converge a light from the sunlight, it converges to a point by a magnifying glass, right? That means whatever size the sun can be, the beam coming from the sun or the image of the sun is just a point. That means the image in this case is very diminished, very, very small, or very largely diminished, you can say. Hugely diminished. Alright, then second one is it is inverted. Why is it inverted? Well, we will consider another case and we will see why we call it inverted, because in this case we don't know how if it is inverted or not, but we will see. Alright, and then the third case, fourth property of the image is that it is formed in the other side of the lens. Other side of the lens from the object. Object is in this case in the left hand side and the image is formed in the right hand side. Okay, these are the properties of the image formed by the convex lens when the object is placed at the infinite distance and we consider the paraxial beams only. Now, we know that when the object is placed at an infinite distance, the ray or the light of the beam of light coming from that object is considered to be parallel beam, right? But they are not necessarily paraxial. They can be coming in other direction also, something like this. They must be parallel but not necessarily paraxial. So this time we will consider the beam of light which is parallel but something like this, but not paraxial. Alright. In such cases, where the ray of light coming from infinite distance, a parallel beam of light also converges to a point. Let's say this is my focus f2 to a point where they will also meet at a point and form the image. In this case, this is the point, let's say, and this point must lie on a plane which also consists of the focus. See, this we can consider as a plane this will be a plane perpendicular to the principal axis, and the focus, the second principal focus, will also lie on that same plane. Such a plane is called the focal plane. Basically, any kind of parallel beam after getting refracted by a convex lens will converge to a point which must lie in this focal plane. Just like the paraxial beam converges to the focus, that is also a point in this plane. Similarly, here if we consider this point as B, this is also a parallel beam, then this parallel beam also converges to a point V which also is a part of this plane. Okay, such a plane is called the focal plane. Okay. Now in this case, see, the object is at infinite distance, image is formed here, again the image is formed by the converging beam. That means the image is of course real, diminished because it was a very huge, let's say something like it was a very huge object. Of course, that is coming from the infinite distance, and the image is very small, that's why diminished. Now see, the object was in the upper side of the principal axis, but the image is formed in the lower part of the principal axis. That's why it is inverted, as I said before, and of course it is in the other side of the lens. Okay, remember one thing, when an image is real, that means when an image is formed by a converging beam, such an image is inverted image. A real image formed by a lens is always an inverted image. Alright. Okay. So this was our first case where the object is at infinite distance. Now let's consider the second point. This time let's draw the points first: the optical center, the focus, 2f, Similarly here, this is F2, this is Q, O, F1, and then P here. Okay, this time we will keep the object AB beyond 2f distance, beyond 2f. Alright, not at infinity but beyond 2f, at infinite distance which is beyond 2f. 2f is what? OP is the 2f distance here. Alright, now we need two beams to form the image. So let's draw two beams. Of course, we will take the two beams whose fate is known. After refraction, we know what will happen. So first of all, we will draw a paraxial beam, which of course after refraction will go through the second principal focus, and then we will take another beam that goes through the optical center. Oopsie, it's a little bit difficult for here in this device for me. Okay, something like this doesn't look so good. Let me try again. Bad. Yes, something like this. Okay, so another beam that goes to the optical center, they will meet at some point here, and then the image is formed. Let's say A prime, B prime is the image here. So AB is the object, A prime, B prime is the image here. So what are the properties of this image this time? When the object is beyond 2f, properties of the image. First of all, again it is real because it is formed by the convergence of the beam. So the image is real this time. Then it is inverted again. As I told you, real means inverted. It must be inverted also. And then again it is diminished because A prime B prime is smaller than AB here, and then it is in the other side also, other side of the object, other side of the lens, as the other side of the lens, and it is between, let me write here, it is formed between F and 2F, where this OF2 is the F distance and OQ is the 2F, right? So real, inverted, diminished, other side of the lens. So others other than the object is in the left side here, where the image is formed in the right hand side here, and then between F and 2F. So these are the properties of this image. Okay, here I must add one property at focus. At focus, the image is formed at focus. All right. Okay, now let's move on to the third case. Third case, where this time we will keep the object at 2f. So the object will be kept at 2f. Okay, so let me draw it here. Then optical center F1, 2f1, F2, 2f2. Okay, So F2 and then Q, P, F1. Object is kept at 2F, means at P. At P. I name the object as AB, and then again we will draw two rays, one of which is paraxial, and after getting refracted, the paraxial beam will go through the focus, and then another one will take another beam which will go through the through the optical center, something like this. This time the object will be formed here, which I will name as, of course, A prime, B prime, which is exactly at the 2F distance but in the other side of the lens. Alright, and of the same size as the object. So what are the properties of the image this time? When the object is kept at 2F distance, the image is real again, because the image is formed by the converging beam, where the beam is converging to a point and the image is formed there. Then it is inverted again. Then of the same size as the object. The image is of the same size as the object, and it is in the other side of the lens, and the size it's at 2F, distance from the optical center. So these are the 5 properties of the image when the object is kept at 2F distance. Alright, now we will consider the fourth case, where the object is kept at in between F and 2F. This time the object is kept in between the focal distance and double the focal distance. Alright, so again let's draw the convex lens, the principal axis. Again we will take the 4 points from the optical center, F2 here, F2 second principal focus, and then at 2F distance Q, and then F1 here at 2F distance P. Somewhere here is P. Now P. We will keep the object between F and 2F, means between F1 and P. F and 2F, between F1 and P. Object A, B, where B is the head. Again we will draw two rays. One of them will be paraxial beam, of course, which after getting refracted from the lens will go through the center, second principal focus of the lens. And then the second one we will draw another one which goes straight through the optical center of the prism, so of the lens, so something like this. Okay, that means the rays will meet here and the image will be formed somewhere here, A prime, B prime. So the image is A prime, B prime. Alright, here clearly the image is formed beyond 2F, beyond Q means beyond 2F, when the object is kept between F and 2F. So what are the properties of the image in this case? First of all, the image is again real, because the two rays actually meet at some point and form the image. Secondly, it is inverted again, inverted or upside down, head is in the downwards direction, right? Alright, object was on the upside, on the upper side of the principal axis, whereas the image is in the bottom side of the principal axis. And then Third is, it is this time enlarged or magnified. See, the image is a little bit bigger than the object. So this time the image is magnified, it is enlarged. And then third, it is again in the other side of the, or opposite side of the lens. And then the last property, fifth property is what? Fifth is, it is beyond 2f. The image is formed beyond 2f. Here was the 2f and it is formed somewhere here. Okay, so these are the 5 properties when the object is kept between f and 2f. So the image is formed which is real, inverted, magnified, other side of the lens, opposite side of the lens, and beyond 2f. Okay. And then the fifth case, where we will keep the object at the focus. As I told you, I am bringing the object from infinite distance slowly towards the lens. Okay, so we started from the infinity, then beyond 2f, then at 2f, in between f and 2f. Now we will consider at f1 on the focus. So at f focus, focal distance. Okay, so let's draw a lens again. Principal axis, this time focus, so f2 here, f1 here. Alright, let's keep the object on the focus, A, B. What will happen to the ray coming from this object now? Optical center, of course, we will draw the paraxial beam, and then this paraxial beam, after getting refracted, will go through the focus. Another ray we will draw straight through the center of the optical center of the lens. This time, as we expected when we keep the object at the focus, after getting refracted by the lens, all the rays becomes parallel to each other. Means they can go whatever distance they want, but they will never meet. Of course, we can consider that they will meet at infinity, at an infinite distance. That means the image in this case will be formed at an infinite distance, right? So what are the properties of the image? Again, we can say it is real because they can meet at the infinite distance. It is inverted again because it is in the other side of the, in the bottom side of the principal axis, and then it is highly magnified. Highly magnified means object is very small and the image is, we don't know where it meets. That means it meets at a very high distance, very large distance from the optical center O, and that will be a huge image. Alright, and then fourth, again it is in the other side or opposite side of the lens. Opposite side of the lens means in the right hand side. And then the last one is what? It is at infinity. So image is formed at infinite distance. Alright, when the object is kept at the focal point. And the last case where the object is kept between optical center O and the focal distance f. This time we keep the object between optical center O and f. That means we bring the object even closer to the lens. Alright, let's see what happens this time. So we will draw it here. Let's see. So another convex, another convex lens, and then this time I draw the principal axis a little bit longer. Let's say this is my focus, f1 and f2, f1, f2. This time I keep the object here. Let's say I keep the object here. Okay, AB. Again I draw a paraxial beam, which of course will go through the focus, second principal focus, after getting refracted by the lens, and then second one we will draw through the optical center of the lens. This time, after getting refracted by the lens, the ray, object AB, the ray becomes diverging ray. See, that means they will never meet. They will never meet. Even at an infinite distance, they will never meet with each other because they are going away from each other. That means a real image is impossible here. Okay, because they have no chance to meet with each other or to converge with each other because they are the diverging rays. So where will the image be formed this time? This time, if we keep our eye here, of course, if we keep the screen here, we can never project the image this time. But if we keep our eye here, if we see from here, we will see this ray, diverging ray is coming from some point, which we'll get if we extend these lines, these rays to somewhere here. So the image will be formed this time somewhere here, A prime, B prime. Alright. So this time the image is not a real image because the image is not formed by the converging ray, but it is formed by the diverging ray, and we got the image only by extending the two rays. Alright, so what are the properties of this image? So when the object is kept between F and O, the properties of the image is, first of all, this is the first time when we get a virtual image by a convex lens. So to get the virtual image by a convex lens, where do you have to keep the object? Between optical center and the first principal axis, first principal focus. And then the second one is where is it? It's not inverted anymore. It is straight or erect. It is erect, right? Because is in the same side of the principal axis as the object. Then third one is it is magnified because the object is bigger than the image. Sorry, the image is bigger than the object, so it is magnified. Then fourth one is it is in the same side of the lens as the object, same side of the lens as the object. And then the fifth one is it is beyond 2f. It is beyond 2f. it is beyond 2f, but in the same side of the lens as the object. Okay, so these are the 5 properties of the image when the object is placed between the optical center and the focal point. Okay, so we have covered all the 5 cases where we bring the object from the infinite distance slowly towards the lens. We first found that we kept the object at infinite distance, the image was formed at the focus, second principal focus, and then we kept beyond 2f, it was becoming the image was formed between f and 2f, and then when we kept at 2f, it was formed at the 2f. Between f and 2f, it was formed beyond 2f, and then when it was at focus, it formed at infinite distance, and between o and f, it formed a virtual image in the same side. So basically, up to f, when we brought the object from infinite distance towards the lens up to f, we got only the real images, and the image started from the focal point, slowly got away from the lens up to the infinite. So slowly we brought the object towards the lens, and accordingly slowly the image went away from the lens, right? Now when we went farther closer to the lens and kept the object between O and F, somewhere here, the image is formed, which is virtual image in the same side. Okay, so these are the 5 cases for a convex lens, the image formation by a convex lens. Now let's move on to the concave lens. Concave lens. For the concave lens, we will consider only 2 cases where the object will be at 2 different places, where first case will be at infinite distance, object will be at infinity, and second case will be where the object will be anywhere which is finite, not infinite, finite distance. Okay, we will see that these 2 cases are enough to see all the image formation by a concave lens. So let's consider the infinite case first. So number 1, at infinity, object is at infinity. So let's draw a concave lens here, something like this, principal axis, then the 2 focus. In this case we will consider the second principal focus, which is here, and the first f1, f2, and the first principal focus in the other side, f1. Alright, so let's consider the object is at infinite distance from here. That means the ray which is coming from the object are paraxial rays, we can consider. Now these rays, after getting refracted by the lens, will become divergent in such a way that they will look like they are coming from the focus, because that's the definition of the first principal focus, right? Second principal focus. So paraxial rays, after getting refracted by the concave lens, will diverge from each other and will diverge in such a way that they will look like they are diverging from the second principal focus. That means the image will be formed at this point here, which will be a virtual image, because the diverging beam will never meet with each other, but they will seem to be converging from this point, which will be the image of the object. That means in this case, what are the properties of the image we can say? First of all, we can say the image is virtual, Second, it is erect, same side of the principal axis. Then third, it is at focus. It is at focus. Fourth is, it is highly diminished. Highly diminished, because it becomes a point object. Alright, and then fourth, we can say it is in the same side of lens as the object. Same side of the lens as the object. Alright, so these are the 5 properties of the image formed by the object which is kept at an infinite distance from a concave lens. Let's consider the second case, where the object is kept anywhere. Let's say between f and 2f. Between f and 2f. Alright, so let's draw a concave lens here, principal axis, focus, 2 foci, and then 2f somewhere. This is the optical center, 2f somewhere here. So let's keep, this is, let's say f1, this is p, f2, this is q. Okay, so let's keep the object between f and 2f somewhere here, a, b. We will consider 2 rays, of course, the paraxial ray, which after getting refracted will diverge and will look like coming from the focus. And then second one we will draw, which will go straight through the optical center of the lens. Now do these rays after refraction meet with each other? No, because they become again diverging rays, so they will never meet with each other. That means in this case also real image is not possible, only virtual image is possible, and virtual image we can get only by extending one of the refracted rays. And we can see that the 2 rays after the extension meet at this point. That means the image of the object AB will be formed here, A prime, B prime. Okay, so A prime, B prime is the image here, which is in between the optical center O and the first principal focus F1. So what are the properties of the image in this case? First of all, it is virtual. Second, it is erect. Third, it is diminished. And then fourth, it is in the same side of the lens as the object, and then fourth, it is between optical center O and first principal focus F1. Alright, so these are the second principal focus, actually F2. This is F1, this is F2, or focus rather. Okay, so between the optical center O and the focus F, or the second principal focus F2. Alright, so these are the properties of the image formed by the object when the object is kept anywhere. Why anywhere? Now if you draw the image by the object when the object is kept anywhere, let's say here, you will see that always the image will be formed between O and F. Always a virtual image will be formed between O and F. Alright, that's why we consider only two cases in this case. Alright, so these are the image formation by the lens. We have considered both convex and concave lenses, where we have brought the object from infinite distance towards the lens, and we have seen where the image was formed by two lenses. Alright, I hope this video was useful for you. We will come back in the next video with some other topics. Till then, take care.